Hello everyone, welcome to a new Dive into C++11 episode. In this tutorial we're going to cover a very common game development topic, which is entity management. I highly recommend watching part 1 and part 4 of Dive into C++ before watching this video. So, let's say we're making an Arkanoid or breakout clone. There are various game elements that the player will interact with. The ball, the bricks, the power-up and the paddle. A possible way of dealing with all these elements is creating a class for every single one of them, with an update method and a draw method, and then use std vectors of unique pointers to manage the lifetime and the behavior of these classes. This is a very simple example. So we have a class for the ball, a class for the brick, one for the paddle and one for the power-up, and they all have their update and draw methods, and inside here we would have our unique implementation of the game behavior for the ball, the bricks and so on. Then we have the game class itself, which will contain all the containers for the game objects. In this case, as I just mentioned, we're using vectors of unique pointers of the game object type. And take notice that we could also decide to use a vector of ball here, skipping the unique pointer. But this can be problematic because in game development, we often want to keep track of specific game object instances, and vectors have an internal memory location that can resides automatically. So if this memory location changes its size, it needs to copy all the existing elements to the new memory location, and all the existing pointers will be invalidated. Then for our game class, we just have an update and draw method as well, and what these methods will do is simply call update for every object of every container, or call draw in the same fashion. As you can probably see, this approach is difficult to maintain because every time we want to add a new game object type, we need to add a new vector of that game object type to the game class, and we need to make sure it gets updated and drawn by adding another loop in here and in here. This is very cumbersome because you can forget to add the lines here. And if there is another developer who wants to expand your game with a new game type, he will have to manually go and edit the general game class. So I do not recommend this approach, but it can be used for appropriate games, and by that I mean very small games with a small number of game element types where you exactly know what you are going to use. Let's move on and check a possibly better implementation of entity management. So what all the different game element types have in common? They all have an update method and a draw method. We can use C++'s inheritance system and runtime polymorphism features to create a polymorphic hierarchy of game elements, and use these features to allow us to store game elements in a heterogeneous way in a single container, so that we do not have to specify the type of the game elements in the game class itself. So a simple implementation could look like this. We will have a base game element class that has a common interface for all the game element types, and we need to define the methods as virtual to enable polymorphism. But what is runtime polymorphism? Let's see a quick example of this C++ feature before moving on. Runtime polymorphism is a C++ feature that allows us to define this hierarchy of classes that share a common interface but different implementations. So if you already know how C++ runtime polymorphism works and what its drawbacks and pitfalls are, feel free to skip this code segment and move on to the next one. I'll show you a simple example of polymorphism, and I'll hope it will make it easier to understand. So every animal will make a noise. This is our common interface. This is our base class. And every time we define a polymorphic base class, we need to define a virtual destructor that can be empty as well, but just defining this virtual destructor will make sure that the right amount of memory is freed when we destroy a polymorphic object, because polymorphic objects carry a vtable, which is basically a table of function pointers, and it needs to be taken into account in memory deallocation, and also derived object classes can have additional fields compared to the base class, and those have to be deleted as well. The idea here is that our animal will make a noise, but different types of animals will make their own noise. The dog will bark and the cat will meow. We need to override the default behavior of the animal base class by defining our own special behavior for every derived type from the base animal class. To do so, we create a method inside our derived classes that has the same name and signature as the original base class method, and we use the override keyword right after the name of the method to make sure that we are overriding a virtual method in the base class. This is an C++11 keyword, and inside this method we will define our behavior for the dog and for the cat. So what we are saying here is basically that the dog is an animal and all the animals make a noise, and the specific noise made by the dog is this one. It just prints bark to the console. In the same fashion, the cat is an animal, and because of the base class, the cat makes a noise, but the specific noise the cat makes is meow. So this is basically polymorphism in C++. Derived classes might have different sizes from the base class because we could have additional fields in here and in here. So it is impossible to allocate them on the stack using the base type. C++ will allow you to write something like this, which basically says that my dog is a variable allocated on the stack of type myAnimal. So the amount of memory allocated here is size of myAnimal, and we are actually initializing it with a dog instance. This will compile, but it will not work properly, as the size of dog can be different from the size of animal, and we can encounter a problem called object slicing. So the way to solve this is actually using pointers to access polymorphic objects and making sure that the memory allocated for the derived objects is the size of the derived object itself. This is another example that actually works correctly. What we do here is allocate memory for a dog and memory for a cat on the stack, and we can access those objects through a base class pointer by actually declaring the pointer here, which is of the base class type, and assigning it to the memory location of the dog and cat and calling the common interface. What this does is actually invoke the overridden behavior. So if we assign the pointer to the dog and then call make noise, bark will be printed. If we assign the pointer to the cat and then make noise, meow will be printed. And this will not have object slicing because the dog and the cat are allocated with their own real size. So accessing them through a base animal pointer will always enable polymorphism if the methods are declared virtual and override. However, the easiest and most common way of dealing with polymorphic objects is using the heap, and that means allocating the derived type instances on the free store and accessing them through an owning smart pointer to the base class. In this case, we are allocating the dog and the cat on the heap, and we're giving ownership of that memory location on the heap to a unique pointer of the base animal class. This will allow us to call our polymorphic methods, and it will automatically free the right amount of memory thanks to the smart pointer and to the virtual destructor we defined in the base class. This is very powerful as it allows us to create a container of unique pointers to the base class that will automatically manage its memory, but will be able to contain different type of animals. And by iterating over the container and calling the methods that are shared between all the animal types, we will get polymorphic behavior. So let me just compile this file and show you that we get the expected output here. And as you can see, the vector has only the type animal in it, but we can put anything that derives from animal in it. So even if in another module someone else would define a new animal type like bird, then we will be able to put it into this vector and polymorphism will work properly. So now that we understand the basics of polymorphism, let's return to our Arkanoid clone example. So what we're gonna do is create a base game element class here with a virtual update and draw methods and a virtual destructor to make sure memory is handled correctly. And our game elements will inherit from the game elements class and define their own overridden update and draw methods, like we did for the animals. Now in the game class, we do not need to store different containers for different game object types. We can just store a single container with pointers to the base game element type, and we can iterate through it and call update and draw, and thanks to polymorphism, the right behavior will be called for every single game class. This is much better. As you can see, the game class is smaller and easier to read, and adding new game element types will not require the game class itself to be edited. This approach, however, has a big drawback. This kind of inheritance-based design does not allow composition, and by that I mean being able to create several small components of behavior and data that can be shared through game objects. Let me show you a possible pitfall of the inheritance-based approach. Let's say we have a game element and we derive an enemy and a friendly NPC class from the game element. Then we have a friendly armored NPC and a friendly armored NPC with gun. And if we want the same behavior for the enemies, and by that I mean we want an enemy that's armored or armored with a gun as well, we need to repeat the behavior on the other side of the inheritance tree, because we have no way of abstracting away the armored component of a specific object or the gun component of a specific object. This is very annoying when we're dealing with objects that can mix and match their properties and behaviors, and it can become very difficult to manage a big inheritance tree where we have repeated behavior on different leaves. A better approach would be separating common behavior and data in small components that objects could be made up of. Basically, our entity would just be a container of components, and components will contain our behavior and data. So if, for example, we wanted to create a skeleton, we would just add the enemy component to the NPC component. If we wanted to create a paladin, which would help the player, we would add the friendly component to the NPC component with the armored component and the with gun component, for example. And as you can see, these components are repeated in various other entities, but we do not have to directly define the behavior in the entities themselves. Everything will be in the component, and the entity will just be a dump container of these components. And this is much more flexible than the inheritance approach, because we can create entities simply by putting components together. To implement our component-based entity system, we need a manager class that will help us manage component and entities, an entity class that will be a simple container of components and will also have some functions to help us get a specific component or check if the entity has a specific component, and a component-based class that will be polymorphic, from which components will inherit. We will use a component-based system where components do not only contain data, but also logic, and this kind of system is easier to implement, and it's a very good starting point to move away from inheritance-based design, but there are more flexible and performant systems where components are only simple containers of data, and another concept, the system, is used to basically iterate over entities that have a certain component signature and perform logic on those entities. So this is a simple diagram of the design we're going to be implementing. We have a manager, and the manager contains many entities, and every entity contains many components. And the components themselves are polymorphic objects that have an update and draw method. So let's start by forward declaring the entity class, as we're going to use it inside the component class. The base component class will have a pointer to the parent entity, and we need to make sure that the right component types can override the update and draw methods by making them virtual, and also that memory will be managed correctly by declaring a virtual destructor. Then we'll define the entity class, which is basically an aggregate of components, and also has some methods that will help us update and draw all of the components and query them. We'll keep track of the state of the entity with a boolean that tells us if the entity is alive or dead, and basically in the manager class we will simply remove all the dead entities using the erase remove if idiom, and we'll also need a way to store the components inside the entity, and in that case we can simply use an std vector of unique pointer to component. Let's define some methods to help us update and draw the entities, which will only iterate through the component vector and call the virtual update and draw methods, and also some methods to query the entity state to check if the entity is alive and to set the entity to dead so that it can be removed from the manager in the next update cycle. What we'll do now is define a method that will allow us to add component to our entity very easily. And we'll take advantage of C++11 variadic templates and in-placement features to directly construct the components in place. So the method will be a template taking t, which is the type of the derived component we're going to construct, and this type will actually be specified by the developer when we call add component, and it will also take any amount of arguments that will be forwarded to the component constructor. We begin by allocating a component of type t, which is the derived type, on the heap, and perfectly forwarding every single argument that we're passing to the add component method to the constructor of the component itself. We then store this heap allocated component in the variable c. The next thing we'll do is set the parent entity of the constructor to the current entity, which we can get through the this pointer. And then we'll wrap the row pointer that we just created into the heap into a unique pointer, and we will move the unique pointer into the components vector. And then we'll just return the C pointer, the referenced, so that we can actually get a reference to the component. Even if the entity class may seem complex, it is conceptually just a container for components, with just syntactic sugar methods to quickly add, update, and draw components. If the entity is an aggregate of components, the manager is actually an aggregate of entities. So the implementation of the manager is straightforward and kind of resembles the previous one. The manager will have a storage for the entities, and again we will use a vector of unique pointer to the entity class. And our update method in the manager will actually start by cleaning up all the dead entities by using the erase remove if idiom that I explained in the first video of the Dive into C++11 series. And basically what this code does is remove all the entities that are not alive from the entities vector. And since they are wrapped into unique pointers, their memory will be freed correctly. Then we will simply loop over all the alive entities and update them. For the draw method, the same will happen, and we will just draw all the alive entities. And then, as the entity class had an add component method, the manager class will have an add entity method that returns a reference to the newly added entity, and basically just allocates an entity on the heap, wraps it into a unique pointer, and then places back the entity into the entity storage. Now let's test our small and naive component-based entity system. So we will simply create a component called counter component, which will store a float number, which is our counter, and this counter will get incremented in the update method of the component every frame by the frame time. And we'll also print the current counter value to the console. We'll also add a kill component, which derives from component obviously, and this kill component will require to be added to entities that already have a counter component that will be taken by referencing the constructor of kill component. And what this component will do is basically check every frame if the cCounter object has reached 100, and if it has, it will destroy the entity it belongs to. To use these components in our main function, we simply define a manager, and we get a reference to an entity that will be created by the manager, and we create the components into the entity and get references to them while we create them. So what we're doing is asking the entity to create a component of type counter component with no arguments in the constructor, and we'll get a reference called cCounter to this component. Then we ask the entity to create a component of type kill component and pass the cCounter reference to its constructor, because if you remember, the kill component requires a reference to counter component in its constructor, and we basically get that into the ckill reference. And here we will simulate a game loop that runs for 1000 frames, and what the game loop will do is simply update the manager with the frame time 1 and draw the manager. So let's try it out in the terminal. So as you can see, the counter component will start from 1, and every iteration of the game loop it will increment until it reaches 100, where the kill component will actually get into this if and destroy the entity it belongs to. After destroying the entity, in the next game loop iteration, the entity will be removed from the entity container via this algorithm, so that the counter and the kill components will be destroyed. And after that, the game loop won't do anything interesting for the other 900 iterations. So the above example works, but there is an annoying issue, which is the fact that the counter component and kill component are tightly coupled, and we actually require to get the reference to the component and pass it into the constructor of the other component, which is pretty annoying. So we need to create a system that allows us to check and retrieve components by their component type from entities, and by using this system we can avoid explicitly passing a reference in the kill components constructor, and it will also allow us to get and check components at runtime. So let's assume that an entity can only contain only one instance of a specific component type. And let's also assume that every component type has a specific ID integer number that will be unique to that component type. So basically the first component type will have ID 0, and the other component types will have ID 1, 2, 3 until n. With these assumptions, we can create a sequence of bits that helps us check whether or not an entity has a certain component type. And basically we just define a component bit set, which is n bits long, and by checking if the bit is 0 or 1, we can check if an entity has a specific component. So with a very efficient bitwise AND, we can check the component signature of an entity. So for example, if we need to know if our entity has both component 0 and component 3, we will just generate this bit set and use the bitwise AND operation with the component bit set of the entity, and if it returns the same bit set that we passed in, we are sure that the entity satisfies this signature of components. Also, since we assign a unique ID number to every component type, we can store component in a linear array so that we can efficiently get the components of a specific type from an entity in O1 time. Basically, this is our bit set, and this will be our array. That will be an array of unique pointer to components, where the 0th unique pointer will point to a component of type 0. Then in index number 1, we will have a unique pointer to a component of type 1 or a null pointer, and so on. Therefore, we can easily say if entity has component with a specific component type as a template parameter, then we can get the component of that specific type and do something with it. So let's implement everything we just talked about. The first step is figuring out a way to automatically give component types a unique ID. We obviously do not want to force our developer or library user to manually assign a unique ID to every component, as that can be cumbersome and lead to errors. But we can use a simple template trick that guarantees a unique ID every time we call a function with a specific type. So what I do now is define a type def for the component ID type, which is of type std size t, and I will create an inline function that will return a unique component ID. And this basically is a function that has a static lastID member inside it, and every time I call the function, it will return the current value of lastID and increment it by 1. So the first time I'll call this function, I will get 0. The second time I call this function, I will get 1, and so on. Now some kind of template magic comes into play. I'm creating another function that's called getComponentTypeID that returns a component ID, and it takes a type of component as a template parameter. What happens is that when I call this function with a specific t parameter, it will instantiate the template, and at the time of instantiation with that specific type t, the static typeID value inside this template function will get initialized with the getUniqueComponentID, so it will be 0, 1, 2, but the instantiated function with that type t will always store the same number, because this is only initialized at the time of instantiation. So when I call this function with the same type t multiple times, I will always get the same value from type ID. Let me prove that to you by defining 3 types that I will very imaginatively call type A, B, and C. And I'm gonna print to the console the component type of A, B, C, and then I'm gonna print the same type IDs by calling the functions twice in a row. What we expect is to get always the same ID for type A, type B, and type C. So let's run this code, and as you can see, I have type A, which is 0, type B, which is 1, and type C, which is 2, and these values will be always the same for the exact type that they are bound to in a certain way. So now that we know how to get a unique ID for a component type, let's implement our composition-based entity system with the bit sets and the arrays. So I create another namespace here to hide implementation details, and I'm gonna also add a static assert here that will make sure the getComponentTypeID function can only be called with types t that are derived from the Componentbased class. Then I will define a constexpr value that will be the max number of components that our engine supports, and this will be used for the bit set and for the array. And to make our code easier to read and more maintainable, I will define 2 type defs, a component bitset type def, which will be a bitset of max component bits, and a component array type def, which will be an std array of component pointers with max components size. In this particular implementation, I actually store row pointers into the array and not unique pointers, and I will actually handle ownership and iteration with the same components vector that we have in the previous implementation, so that we do not have to check during the iteration of array if the pointer is actually pointing to something or is null pointer. And this is basically an optimization of the iteration of the component vector. The array will just be useful for component retrieval. So to check if the entity has a specific component, we will have a template method called hasComponent that will return a boolean, and what this does is simply ask the bitset if the bit at the position with the type ID of the t-typed component is set to true or to false. To add a component, I also use an assert here to make sure that we do not mistakenly add a component of the same type twice. And also, after doing everything we were doing before, I also set the component array pointer to the newly created component, and I also set the component bit set to true in the bit that represents the unique ID of the component. I also added a new virtual void to the component that is called init, that will call right after adding the component to the entity, so that we can basically retrieve all the required components. This is the virtual void definition in the base class. To get a component of a specific type, again we will use a template function that takes the type T of the component, and it will assert that we have the component inside our entity and retrieve the pointer from the component array with the type of the component ID as the index, and return that component casted to the derived type, because we are sure that the pointer is actually pointing to the derived type, and dereference it for convenience. The manager is exactly the same as the previous implementation, and now we can see the difference in our component implementation. Instead of having a constructor that takes a reference to the counter component here in the kill component, we can simply override the init method and get the cCounter component directly from the entity by using the getComponent function, which is much more convenient and cleaner than what we had before. Now, when we create the entity, we do not need to get the references to the components anymore, and we can simply say add component counter component, add component kill component, and the init function into kill component will automatically get a reference to the counter component without having the user to manually and explicitly do it in the constructor. If we run the code, the result will be exactly the same as before. In my opinion, this approach is cleaner and more efficient than the previous one, because retrieval of components is very fast thanks to the array, and it is also more elegant in a way because we do not have to explicitly handle coupling between the components, and they can just deal with that themselves. Also, the asserts that we added in getComponent and addComponent will make it very easy to understand if we are trying to query a component that is not present in a specific entity, so it's also a safer approach. Let's actually re-implement the Arkanoid clone that you have seen in the first episode of Dive into C++11 and in my CppCon talk with this system. But before we can do that, we also need to add another feature to our system, which is grouping. This feature will allow us to give entities one or more groups, and the implementation will be very simple. It will be just a bit set that will indicate whether or not an entity has a specific group signature. So I'm gonna create a type def for the group, which will be a simple std size t type def, and I'm also gonna create a type def for the bit set, which will be a bit string of n, where n is the max groups, and that's another context variable. In our entity, we will need a reference to the manager, as the manager will actually store entities divided in groups in an efficient array for easy retrieval, and also it will need the group bit set itself. We will add some functions that can help us check whether or not the entity belongs to a group, and that's simply done by checking the bit at the m group index, in the case of has group. Adding the entity to a group will be more complex because we will need to notify the manager of this addition, and the manager will need to handle it and add the entity to a specific bucket so that we can easily retrieve all the entities of the same group with a very good performance. To delete the entity of the group, we will simply set the group bit to false, and there's no need to notify the manager here, as we will automatically remove entities from the wrong containers before the update during the refresh. So now let's check the new manager implementation. We will have an array of vector to entity pointers with max groups slots basically, and those will be our buckets, where every bucket will store all the entities that belong to the same group, and I'll call this container grouped entities. When an entity is added to a group, it will ask the manager to add itself to the correct bucket by passing a pointer to itself and the group that it has just been added to. And what the manager will do is simply add the pointer to the correct bucket in the grouped entities container. In the refresh method, which will always be called before the update method, before erasing the dead entities from the main entities container, which is this one, we will need to remove the entities that do not belong to the right groups. And to do that, we simply iterate through every bucket in the array of grouped entities, and we call the erase remove idiom into that bucket, removing all the dead entities and all the entities that do not have the right group. Now we need to define the addGroup method of the entity that we just declared in the class here. And the definition is very simple. We will set the group bit set bit to true, and also ask the manager to add this entity with this group to the group buckets. The rest of the program is the same, because we do not use grouping in this example, but we'll use it in our re-implementation of the Arkanoid clone. So to begin, we need some additional includes. We're going to use chrono for the frame time and functional for some callbacks, and we'll also use SFML for the graphics and the input management. This is our component-based system that is exactly the same as the previous code segment. And now, from line 188 onward, we will re-implement our Arkanoid clone. I'm going to skip over the logic details of the game, as we have already discussed them into the first episode of this series. What I'm going to do is analyze how we divide the entities into components. We'll start by having a cPosition component that basically has a position value and some methods to retrieve the x and y coordinates. Entities can have a position in the game world, so it makes sense to have a position value in a single component. Also, entities can have a physical body and a velocity, like the balls and the paddle and the bricks. So we need a cPhysics component that will require a position component and also have some data, which is the velocity and the half size of the entity. We'll also use a callback using std function, which is basically a type erasure wrapper for generic functions that will be called when this entity goes out of bounds. So we can handle this event for the ball, for example, and make it bounce. The cPhysics, as I just said, will require the cPosition component, so we override the init method and get a reference to the component from the entity. In the update method, we will basically handle the physics and call the out of bounds callback in case our entity goes out of the window of bounds. And we'll also have some convenient methods here to get the left, right, top and bottom coordinates. An entity can have a circular shape or a rectangular shape, so I'm going to create a circle component and a rectangle component that will handle the drawing and the position of the shape. We only require cPosition as a requirement and not cPhysics, because we do not care about the sides or the velocity of the shape. We will handle that explicitly, but we will always update the shape to be in the position of the cPosition data. Next, the user control paddle needs a special component to handle keyboard input, and this actually requires cPhysics because we're going to explicitly set the velocity of the paddle, and in the update method of the cPaddle control component, we query the keyboard state and change the velocity of the physics component based on the keys that are being pressed. Then here we have some logic for the collisions. Basically, these functions want some entities as input parameters. In this case, we want the paddle and the ball. And what we're going to do is get the cPhysics component both from the paddle and the ball and do some testing here and some collision resolution. And we'll do the same for the brick and the ball. As you can see, we're simply passing entities in here, but what we actually need is the cPhysics component, which will be retrieved via the getComponent method. In this case, when the brick collides with the ball, we will also destroy the brick entity so that it can be deleted in the next update cycle. In the game class, we will use an enum to keep track of the entity groups, and these groups will be the paddle, the brick, and the ball groups. Creating entities can be done through simple factory functions now. Basically, we will create a ball by returning an entity reference, and inside the function, we will create a new entity thanks to the manager. We will add some components to that manager. In the case of the ball, we will need the C position, C physics, and C circle. And by getting a reference to the C physics component, we can set the initial velocity and the callback for on out of bounds that will make the ball bounce when it hits the window sides. Also, we'll add the group gball to the entity. The brick and the paddle are basically created in the same way. We simply create an entity, add some components to it, and the group, and return it. As you can see, this is very convenient and expressive, because creating entities is just putting them together from components. This is all the logic for the frame time and input that I've explained in the previous Dive into C++11 videos. Something new is here in the update phase. Basically, after updating all the entities, we get from the manager the entities by group. We get all the paddles, all the bricks, and all the balls, and perform some collision tests on them by calling the specific function. In this case, test collision PB will test the P, which is the paddle, against the B, which is the ball, and this one will test the bricks against the balls. So let's try out this implementation of the Arkanoid game, which will play exactly the same as the previous one. Here it is. And I hope you enjoyed this tutorial and that you experiment with component-based design, as there are very flexible ways of implementing your game objects, and it's a very interesting programming problem to figure out a performant and flexible and convenient way to easily create flexible entities and components. Thank you for watching. Do not forget to check out a video I published around a week ago about handle management, which is very interesting because it can be applied to component-based entity systems.